All right, let's dive in. This research paper you sent over about the neural data booter, NDR, is super interesting. The thing that really grabbed my attention is how it's going after this huge problem in AI, how to get networks to learn rules and apply them to brand new situations instead of just like regurgitating what they've been trained on.
Yeah, exactly. It's that whole question of systematic generalization. Can a network actually get the logic and then use it in a way that goes beyond just the examples it's been fed? This paper is diving right into that, specifically with transformers, which have obviously been making a lot of noise, particularly in natural language processing.
For sure. And from what you've pointed out in your notes, it seems like the NDR is focusing on this challenge, but in the world of algorithms and tasks where you need a very specific set of steps to get to the right answer.
That's the heart of it. The authors of the paper, Csordás, Irie, and Schmidhuber, they point out how standard transformers, they're impressive in lots of ways, but they often trip up when it comes to tasks that involve a very specific sequence of operations. Like think about solving math problems or understanding computer code. That's where the NDR comes in with these very clever modifications.
Okay, I'm definitely intrigued. So let's break down what the NDR actually brings to the table.
Well, the researchers introduced two really key innovations, the copy gate and geometric attention. Think of the copy gate like a traffic controller inside the network. It basically lets the NDR decide whether to process information at each step or just pass it along untouched to the next stage.
So it's almost like the network is learning to prioritize, figuring out like which bits need attention right away and which can wait a little bit.
Exactly. This ability to control the flow of information, it's essential because it lets the NDR learn the best order of operations for a given task. And here's a fascinating thing. That copy gate, it starts off biased towards skipping processing, almost like it's pushing the network to find the most efficient path.
So that is really interesting. Almost like giving the network a nudge to be a little lazy at first and then see if it can figure out the shortcuts. Okay, so we've got the copy gate correcting traffic, so to speak. But what about geometric attention? How does that fit into all of this?
Geometric attention is all about focus. It helps the network zero in on the most relevant information at each step. Like, imagine you're reading a sentence and you come across a pronoun like he. To figure out who he refers to, you naturally look back in the sentence for the closest noun that makes sense, right? Geometric attention is similar. It prioritizes attending to the closest matching elements in the input, which helps the NDR process things in the correct order.
So it's like instead of getting distracted by every possible connection, it just keeps its eye on the most immediate, the most relevant piece in the puzzle.
Exactly. And here's the crucial difference from typical attention mechanisms. Geometric attention really encourages the network to focus in on that near match and downplay the ones that are further away. This is super helpful for tasks where the order of the steps is critical, like algorithms and structured computations.
Okay, so we've got the copy gate directing the flow and geometric attention, keeping everything sharp. But how do these innovations actually translate into, better performance? Did they actually put this NDR to the test?
They did, and the results are pretty impressive. They designed three tasks to really challenge the NDR's systematic generalization abilities: compositional table lookup, simple arithmetic, and ListOps.
Okay, now I'm really curious. Let's break down those tasks and see how the NDR stacked up.
Let's start with that compositional table lookup task, CTL. It's a really good way to test how well a network can actually learn and apply rules. So imagine like you have a set of rules, kind of like if you see symbol A, then apply function X, and then apply function Y. The network needs to learn these rules and then be able to use them correctly, even when the sequences of these symbols and functions get longer and more complex than what it saw during training.
Okay, so it's not just memorizing what happens when you combine certain functions. It's got to really grasp that underlying logic and be flexible, right?
That's exactly it. And to make it even trickier, they actually tested two versions of this task, forward and backward. In the forward version, the input is given in the same order that the functions should be applied, like AXY. But the backward version, they flipped it around, so it'd be like YXA, but the network still has to figure out the correct order of operations.
That sounds pretty tough. Did standard transformers have a hard time with that?
Yeah, they did, particularly as the sequences got longer. It's interesting, though, LSTMs, another kind of neural network, they actually did pretty well on the forward version. They could generalize to longer sequences, no problem.
Huh. So maybe the way LSTMs are designed, their sequential nature, gives them a bit of an advantage in that specific scenario.
It's possible, but here's the thing. LSTMs totally failed on the backward version. They couldn't handle the reverse input order at all. Now, bidirectional LSTMs, which process information in both directions, they aced both versions, forward and backward.
Right, that makes sense. They're not as thrown off by the order because they're kind of looking at the sequence from both ends.
Precisely. But while bidirectional LSTMs work great for this specific task, the researchers were really going for a more general solution, something that could handle a wider range of problems where the processing order might not be so obvious. And that's where the NDR really shines.
So how did the NDR do with that backward version of CTL? Did the copy gate and geometric attention stuff we talked about actually make a difference?
They absolutely did. The NDR got a perfect 100% accuracy on both the forward and backward versions, even on those really long sequences it had never seen before. The visualizations they made are super insightful. You can actually see that copy gate holding on to those input symbols, keeping them unchanged until it's their turn to be processed. And at the same time, that geometric attention is letting the network focus, like a laser, on the right function to apply at each step no matter what order they come in.
So it's not just blindly following along, it's actually deciphering the logic behind it, which is pretty amazing when they think about it.
That's exactly what systematic generalization is all about. It's not about just memorizing things, it's about understanding the rules.
Okay, so the NDR nailed the CTL task. What about that simple arithmetic one? How did it handle those nested operations and parentheses that can really trip things up?
This is where things get even more interesting. This simple arithmetic task, it's a step up in complexity because it requires the network to deal with something called tree-structured data flows. Think about how we solve a math problem, like 2 plus 3, 4. We don't just go from left to right, right? We solve what's inside the parentheses first, then we multiply. That creates this hierarchical structure, kind of like a tree, where different operations depend on the results of calculations that came before.
I see. So it's not just a straight line. The network has to understand how different parts of the expression are connected, those dependencies.
Exactly, and that's a big problem for a lot of standard neural networks. They have a hard time with these long-range dependencies, where something that happens way back in the sequence might actually be needed for an operation that comes later.
So how did the NDR approach this challenge? Did the copy gate and geometric attention play a role here as well?
You bet. The NDR once again showed near perfect accuracy, even when the expressions got more complex than what it was trained on. And the visualizations, it's really cool. They show the NDR learning to actually process the input in the correct order, respecting those hierarchical dependencies.
Wow. So it's not just applying operations as they appear, it's actually figuring out what needs to be done first based on the structure of the problem.
Exactly. It's almost like it's developed this internal understanding of how those map expressions work.
I'm starting to see why this is such a big deal. It's not just about beating other networks. It's like a new level of reasoning that we haven't really seen before.
That's a great point. It's showing signs of real systematic generalization, not just memorization or some clever pattern matching. Okay, so that brings us to the last task, ListOps, which is probably the most difficult of the three. This one involves nested lists and operations like min, max, and median.
Right, the one with those lists within lists where the network has to apply these operations at different levels. Sounds like a recipe for disaster, honestly.
It can be, but it's a great test for seeing how well a network can handle these complex hierarchical structures. It's not just understanding the individual operations, it's about applying them in the right context based on how those lists are structured.
So how did the NDR do against this ultimate test?
Well, once again, it rose to the challenge. It achieved near perfect accuracy, even on lists that were more deeply nested than what it was trained on.
I think I'm sensing a pattern here. The NDR just keeps exceeding expectations when it comes to systematic generalization.
And that's the really exciting thing about this research. What's especially interesting about the ListOps results is that the visualizations actually reveal some pretty neat insights into how the NDR is tackling this task. It seems like different attention heads within the NDR are specializing in different roles.
Hold on, different attention heads. I thought attention was just one mechanism.
So in transformers, you actually have multiple attention heads working at the same time, each one focusing on different aspects of the input. It's kind of like having a team of experts, each with their own specialty, working together to solve a problem.
Okay, that makes sense. So what were these different attention heads up to in ListOps?
It looks like some of the heads are specifically focused on figuring out the operators like min or max, and then figuring out the right arguments, the things they should operate on within those nested lists.
So they're basically working out which numbers or sublists each operation should be applied to.
Exactly. Meanwhile, other attention heads seem to be busy copying the results of those intermediate calculations to the right spots within the whole structure. It's like this really well coordinated dance where different parts of the network are working together to process the information accurately and efficiently.
So they're making sure that information flows in the right direction, going from the deeper levels of nesting up to those higher levels.
That's right. And then you have the copy gate, which seems to be controlling the timing of these operations, like making sure that calculations only happen when all the necessary inputs are ready to go.
It sounds like the visualizations are showing the NDR actually taking advantage of the way ListOps can be done in parallel, processing different branches of that computation tree at the same time.
It is. That's one of the reasons it's so efficient. Once those deeper calculations are done, the gates open for the higher levels, and the whole process continues until the entire structure is processed.
This is really impressive. It's like we're seeing a neural network that isn't just crunching numbers, it's actually understanding the structure of the problem and then executing a plan to solve it, almost like a form of reasoning.
You got it. The NDR is showing a level of sophistication, a level of reasoning that goes beyond what we've typically seen in those more traditional architectures.
So we've seen how well the NDR does on these three very different algorithmic tasks, showing that ability to generalize consistently. But let's zoom out for a second. What does all this mean in the bigger picture? Why should we, as humans, be excited about a neural network that can do math and list operations really well? What's the broader significance here?
And that's the real question, isn't it? And that's what we'll dig into in the next and final part of our deep dive.
All right, so we've talked about how the NDR is really shaking things up when it comes to those algorithmic tasks. It's showing this ability to learn and solve problems that goes way beyond just recognizing patterns. But let's step back for a minute and look at the bigger picture. Why should we, as humans, get excited about a neural network that's super good at math and working with lists? What does it all mean?
That's the million-dollar question, isn't it? The really cool thing about the NDR is that it's not just some niche tool for solving these specific isolated problems. It could potentially change the whole game when it comes to artificial intelligence and what it can actually do.
So we're not just talking about making things a bit better, we're talking about a fundamental shift.
Yeah, possibly. The big challenge that the NDR tackles is systematic generalization. How do we create AI systems that can learn and use rules, not just memorize patterns? This research is pointing towards a future where AI isn't just a tool, but a truly intelligent collaborator.
Okay, that's a pretty compelling vision. So give me a picture of that future. How could the NDR or the ideas behind it actually change the world? What are we talking about here?
Well, let's think about those fields we touched on earlier, like robotics and natural language processing. Imagine robots that can really understand their surroundings and adapt to new situations, not just follow a bunch of pre-programmed instructions.
That would be huge for so many industries. Manufacturing, healthcare, even space exploration.
Right. Self-driving cars that can handle crazy traffic situations they've never seen before, or robots helping surgeons with incredible precision and the ability to adapt on the fly.
And when it comes to natural language processing, we could finally have chatbots and virtual assistants that actually get what we're saying. They could have real conversations with us, not just spit back canned responses.
Exactly. Just imagine talking to an AI that feels as natural and nuanced as talking to another person.
It's pretty mind-blowing when you think about it, but it sounds like this could go even further than these specific examples, right?
Oh, definitely. The fact that the NDR is so successful with these algorithmic tasks, it suggests that it might be able to learn a much wider range of skills. Anything that can be broken down into logical steps could be within reach.
So it's not just math and list. We're talking about things like programming, scientific research, maybe even creative writing.
That's it. If we can teach AI to understand and use rules in those kinds of domains, the possibilities are pretty amazing.
This is where it starts to sound like science fiction. AI writing software, designing experiments, even composing music.
The NDR is giving us good reason to think that maybe those scenarios aren't so far-fetched after all.
It's exciting stuff, but it's good to remember that this is still early days for the NDR, right? There's a lot more research that needs to be done.
Absolutely. This paper is really just the first step on a very exciting journey. There are still plenty of questions to answer. How do we make the NDR bigger and more powerful to tackle even more complex tasks? How do we make sure that its decision-making is transparent and accountable?
Right, we have to make sure this technology is developed and used responsibly. But even at this early stage, the NDR paints such a compelling picture of what AI can become.
It's a good reminder that AI isn't just about building machines that can do things faster or better. It's about understanding and replicating the core of intelligence itself.
And that's something that should excite and inspire us all. It's about seeking knowledge, seeking understanding, and looking towards a future where humans and AI can work together to solve some of the biggest problems we face. Well, this has been a fascinating deep dive into the neural data leader. What an incredible journey. I can't wait to see where this technology takes us in the years to come.
Me too. It's really exciting to think about the possibilities. And to everyone listening, I encourage you to dive deeper into these ideas, question the assumptions, and dream big about what AI can become, because the potential is truly extraordinary.